Wow, hello everybody. Can everyone hear us? Nice to see so many faces. Jackson, our co-instructor, is going to join us in 2 minutes. So if you want, there's a live transcript is enabled. You can click to see the live transcription of what's going on here. It's so nice seeing all of you here. This is so cool. So this is the first class of a Fiat Lux seminar, which is a special seminar offered to UCLA students. But we're so happy that we're making this seminar available to anyone in the internet. And it's going to be super cool because we don't require any prior quantum mechanical knowledge. After 2 classes, Introduction to Quantum Computing, Introduction to Quantum Mechanics, and Introduction to Quantum Computing, we are going to talk about different flavors of quantum computation, right? And I think that quantum computing is like a buzzword that many of us are hearing around. So I'm super happy that we can now share a little bit of our work and a little bit of quantum computing with all of you. And Jackson is here, so I'll let her take it away.
The room absolutely keeps filling with people. I'm gonna pretend like that is totally okay with me and I am not nervous at all. But hello, everybody, welcome. For those of you who are actually enrolled in this class, hello, welcome. Thank you for joining us on this first day of the spring quarter. For everybody else who is a guest here, who's not receiving credit for the course, hello and welcome. We're happy to have you. For the students, I just want to have some housekeeping. If you could just turn on your cameras if you're able. I like talking to people I can see. It's strange to talk to a whole bunch of names on the screen. So if you could just turn on your cameras if you're available, even those who are not students, make sure you stay muted. We do have subtitles available, so if you click on subtitles, they should be able to come up. We won't have an issue with that. Students, there is some housekeeping we have to take care of in the beginning, and then for everyone else, just sit tight. I will get to the quantum shortly. We just have to start with a few things for everybody to know. So it's 12:04, so let me go ahead and get ready. Take a deep breath. It's raining here. Thankfully, it calms me down. Can I get a thumbs up if you can see my screen? Beautiful. All right, if anybody has any questions, go ahead and jump in the chat. Let us know if you have any issues hearing me, seeing the things that I'm presenting. No worries, but I am gonna start while Clarice continues to admit people. So welcome everybody to the Electrical Engineering 19 class, the Freshman Fiat Lux series. The title of this course is My Favorite QuBiT, Quantum Computing as Told by Leading Practitioners. This class meets every Monday at 12 p.m. Pacific on Zoom. There is an asterisk there because we do have one person on our list who may show up in person, and they are an amazing quantum scientist. So we will let you know at least a week in advance if this, hopefully, fingers crossed, that they let us know that we will be meeting in person, but all lectures will be recorded and posted to our YouTube channel. So if you can't make it, that's okay. We will definitely take care of that. So for the student housekeeping, just a quick meet the team. So you all have met Clarice, the lovely woman who brought you into the room. I am Jackson Fletcher. Clarice is the assistant professor and the instructor for this course in the Electrical and Computer Engineering department. I work with her. I am a first-year PhD student in the same department, and I am the co-worker for the 2022 Spring Fiat Lux series.
You can drop the co. You're as an instructor as I am, so you have.
I'm here, guys. I am here. So we will go with that. So what I want you all to know first and foremost is that in this Fiat Lux, participation is strongly encouraged. This goes for guests and students. We value participation, so we may use polls in this class. We may have you use the raise your hand function. We may ask you to post your questions to the chat, and we may do something that we call chatouts, which are very fun and interactive. So the purpose of a chat out is I'm going to ask you a question, and then once you see the prompt, you're going to type your response to that in the chat. And you're going to wait. We're going to give it about 30 seconds for everybody to put in their answer. And then we're going to press enter when I say so. And the chat should flood. And I should see everybody's responses to whatever question I've asked. So we're going to test this out. And you're going to see a few of these throughout the lecture. And I just want to know, we have so many people in the room. Where are you all joining us from today? What city are you in? So don't press enter yet. Just go ahead and type your response. And we'll just give it a couple of seconds. All right, so we're gonna press enter in 3, 2, 1. Press enter. Let's see where everybody's from. Oh my gosh, they are from everywhere. I don't even know where that is. I say St. Paul's, Mayagüez, Chennai, Connecticut, Vancouver. Oh my goodness. The UK, India. Oh my goodness. Thank you to everybody who has tuned in today from all over the world to see us talk about quantum and why we love it so much. I thank you for all of that. For the students, very quickly, this is also on Canvas. So if you're not in Canvas, go ahead and get there. There's just certain learning outcomes you all should be familiar with. You should be able to enumerate some weird quantum mechanical properties of matter and light at very small scales. Basically tell us what quantum is, explain the concept of a quantum bit or a qubit, give examples of different qubits, which people will discuss later throughout the seminar, compare and contrast the functioning of different quantum computing implementations, provide examples of how scientists and engineers can have a career in quantum, and discuss the societal implications of quantum mechanics and quantum computing. So these are all things that will not be touched on today. This is just a very rough and tumble introduction into quantum mechanics. And when I say rough and tumble, I do mean rough and tumbles. There's no math. So if you've never taken a quantum mechanics course, there are just a few things I want you to know, but we're going to keep it very simple and very basic. This is just the week of the schedule of lectures coming up. So today, of course, I'm doing the intro. We have Hunter Solomon coming from the coding schools, QuBiT by QuBiT Academy. We have people coming from IBM. We have other PhD students coming in, a bit of everyone. Guys, my mom is coming into this room. I just saw her name on my screen. My mom is here to watch me present. I don't even know what I'm going to do. Hi, mommy. Okay, so continuing with Lindsay LeBlanc, Shara Selden, even Clarice is going to give a wonderful talk week 8. Week 9, we're going to have a panel discussion, and week 10, that actually is a holiday, so there'll be no class. However, because there are some requirements for your final, there are 2 bonus sessions that you can come to. So even though we're recording them, if you want to see a little bit more about some quantum computing, there are 2 extra talks. One is given week 7 and one will be given week 9. Okay, so make sure you tune in and join us for those. We're super excited to have all of these wonderful speakers coming in. Students, for the final exam, you're going to get a summary table. You'll see the directions for that in Canvas, and then you'll just have a 1-page essay with the prompt about your favorite qubit and how quantum mechanics and computing can alter society and the world that we live in. All right, so simple to the point. All the housekeeping is out of the way. Again, my name is Jackson Fletcher. It is a pleasure to meet all of you, and to present this to you, I want to talk about a bit of quantum mechanics. And I'm going to hide this silly control screen because it keeps getting in my nerves, in my way and on my nerves. So, intro to quantum mechanics. So this graphic, right? We have must be and we have can't be, but somehow in the middle, it's real. Both of these worlds coincide. And I actually got this from a New York Times article from a book written by Dr. Andrew Beck. He is a PhD out of the University of Michigan, I believe, and he has a book about quantum mechanics. But I want to talk about the difference between the must be real and the can't be. And it basically, we're getting into classical versus quantum ideals. There are vastly different thoughts in these 2 schools of knowledge. All right, so with classical physics, also known as Newtonian physics, we have predictable motions. What do I mean by predictable motions? Well, it helps us a lot. We can know where things are and how fast they are going at the same time. Think about launching a satellite. I need to know those two things if I'm going to successfully launch a satellite. I do not want to launch a satellite and put it into space and then have no idea what's happening. And that should only happen should the GPS fail. But I can launch a satellite, I can know where it is in space, and I can know how fast it's going. When I get into what seems like it can't be, the quantum mechanics of it, quantum becomes very unpredictable very quickly. I can know how fast a particle is going, but I can't tell you where it is. I can give you the probability of the space it might occupy, but I cannot say it is exactly right here, because that's not how particle physics or quantum mechanics work. Newtonian deals with macro scale, big objects, us. We're a macro scale object in physics, okay? So us, our cars, our homes, the earth, the sun, the planets, big things. We're dealing with microscopic objects in quantum, and those objects can be the billionth of a diameter of a human hair. They're extremely tiny. So we're going from big, predictable to extremely tiny, doing whatever they want type objects here when we're talking about quantum. And another really important thing we have is that in classical physics, things are continuous. And I'm going to talk a little bit about what that means a little later. Whereas we work in discrete packets of information when we are in the quantum, but somehow both of these things come together and actually create the world that we live in. And I love it because I know that when quantum was starting to become more valid and science was starting to prove what these things were, I know that these scientists were so confused because they had this classical understanding of physics, and then here comes some wonky observation that doesn't even begin to make sense or logic. And then some other people had to come and help us figure out what we were looking at, but somehow it all works together for the world we live in. So I want you to know that even though quantum is a really big buzzword in science right now, it's like STEM. When I was in college, STEM wasn't a word. As soon as I graduated college, everyone was like, oh, science, technology, engineering, and math. And it was like the biggest buzzword. And I was like, it's just science. It's always been the science, technology, engineering. It's always existed, but we just needed a word for it. So now quantum has always existed, but now there is a slew of people who are interested in it. But don't let that make you think that it's something brand new. It's been around for quite some time, and it's in our everyday lives, and LEDs, MRI machines, magnetosensing, which is what my research focuses on. I study magnetosensing in migratory species, electronic communication. All of these things revolve around the quantum world. Okay, so it's a buzzword right now, but it's something that we have been dealing with for quite some time. So I want to go through a brief history of science here. Okay, too far. All right, so briefly, 1500, Copernicus said, hey, I want y'all to know the Earth is the center of the universe. Okay, bye. And for a long time, everybody believed that. They said, oh, the Earth is definitely the center. It revolves around us because we're man and we're the greatest thing that's ever been created. And then Galileo, and around the 1600s, said, no, excuse me, no, I believe it's a heliocentric universe, which means we revolve around the sun, as do the rest of the planets. Well, at this time, the Catholic Church said, absolutely not. Don't say that. You are on house arrest. Stop telling people that. And Galileo was like, okay. And then he wrote all of books telling all of the people, all of the things about the heliocentric universe. And he actually ended up dying on house arrest because the Catholic Church wasn't having it. In the 90s, they did apologize though, but he was a little past pasture then. But from there you get Kepler, who gives us the laws of planetary motion. And then a lot of math is done. And then we're all familiar with the Hermit of Cambridge, Sir Isaac Newton. So Isaac gave us Isaac gave us our three laws, which really dictate the classical mechanics world, right? The first law being an object going in a straight line, constant velocity, will continue in motion unless acted on by a net force, or an object staying still will stay still unless acted on. So the water bottle that's on my desk should not for any reason just fly off of my desk without any net force. Now, should this water bottle fly off the desk, I will be leaving this house immediately and this meeting will end, okay? Because that's a ghost and I don't do ghosts. So don't have to worry about that. But the second law is F equals ma, and we all know that if we apply some force to an object with mass, it should accelerate in the direction, right? So if I push on a door, the door should move outwardly. The door should not fly back and hit me in the face. That would defy classical mechanics. And then the third one, for every action, there's an equal and option reaction, which is the reason I'm not falling through this chair and my laptop isn't falling through the desk. These are very tangible laws This is one of the main reasons, because we spent so much time studying the things that we could see and the things that we could touch. This is one of the reasons why quantum mechanics just did not seem to make any sense, because it just brought about the question of, why is this happening? And why can't I see this happening? Okay, so we get into a whole bunch of other people, Einstein, Boltzmann, Schrodinger, Maxwell, all of these amazing things. And all of this amazing science was brought by all of these people. But one thing I do want you to notice about these scientists is that this is a very homogeneous group, right? And one of the main purposes for the Fiat Lux is to show you that science is not this homogeneous, or should not be this homogeneous. Now, given for the time, for the rules around education and who could go to school and who had the ability to learn, it makes sense that a lot of the scientific breakthroughs were brought through by this group of people. But I'm sitting here, and then all of the other speakers you're going to see are coming, because we're gonna disrupt a lot of the homogeneity that you might be used to when talking about science and these discoveries and who's doing the work to move us forward. So going back, what I really want to start with is, it took place in the 1900s. Now we're going to go forward and then backwards, because a lot of people think what happened in the 1900s is super important, but I think what happened in the 1800s is far more important, but you'll see what I'm talking about in a minute. So we're going to start with the ultraviolet catastrophe. All right. Well, you all know it as the ultraviolet catastrophe. Clarice and I like to call it the ultraviolet catastrophe prediction, because it's based on the prediction made by Sir Rayleigh and his research partner, James Jean, who were studying black body radiation. Okay, so black body radiation simply says that an object should absorb a certain amount of energy, and then it should emit the same amount of energy. It should work with the law of conservation of energy. What goes in is what comes out, right? So they were doing the math because they were like, this is what we do. We're going to show this, match this theory to the experiment. And for some of you, a clear illustration of black body radiation can be seen here in this image of a piece of metal that's being heated up. All right. The metal glows, and that glow directly corresponds, the amount of light it emits is directly corresponds to the temperature of that piece of metal. All right. So they should directly correlate. But the thing that ended up happening was, when they did the math, something was really wonky. They were noticing that they would put a certain amount of energy into the system, but they were getting back an infinite amount of energy. And that defies the law of conservation of energy. You can't do that. I can't put in, just an itty bitty piece of energy and then get back infinite energy. The world would be drastically different if that would happen. So what you should be paying attention to is this gray dotted line, right? You can see it just diverging all the way up to infinity. And they were like, oh my gosh, what is happening? We can't explain it, because they were really using a lot of classical math to define what was taking place here. Well, the good news about science is that while you were studying a thing, chances are there is another person studying the same thing, but for different reasons. So Planck was also interested in black body. However, what Planck wanted to know was, why does heat flow from hotter objects to colder objects? This is really what he was studying. And he was looking at the same math and he was going, this is weird, because this infinity thing is just, I don't like it. He said, so I am going to postulate. I'm going to make a postulation here that's going to fix the infinity, because it's just not going to work. So what he actually postulated was that a black body could only emit light in discrete quantities. And there's that word discrete again, right? And so by saying a black body could only emit light in discrete frequencies or discrete quantities, he was able to match the theory to the observation. So what he ended up doing to make the math work, instead of getting an infinite amount of energy out, is he said that all the frequencies that we're looking at are discrete packets of frequency. There are certain numbers, and in order to normalize them or to make them not equal to infinity, what we need to do is there has to be some constant, right? And so he basically like plug and chugged his way to victory. And he said, this is the constant I give you that will make everything stop going to infinity. I postulate that there is some constant named after me, of course, because I found it, Planck's constant. That is this number, 6.626 times 10 to the minus 34 and some units. And that is what is going to give us our energy. And we still abide by this function today. So this H is actually Planck's constant, as you can see, blue to blue. And we're most familiar with this equation, e to the HF. It's just written backwards here because I didn't want to confuse anybody by switching it midway through. All right, so what he did here by introducing this constant and these discrete quantities is he made the theory match the observation, so it no longer shot up to infinity. Now it started to make sense, and we thank Planck for that. So this actually initially, this idea of quantization began to lay the work for quantum mechanics. And in discrete packets, it's how I said earlier, in classical physics, we have a ramp. I can go from values 1 to 5, but I can also have these continuous numbers where I can have 2.5, I can have 3.7. But as I told you, it's like people in your house or in your room. You're not going to have 1.5 people in your house. There's not 1.5 students in this class or 20.5. There should be 20. And so what Planck said is that you'll get 1 packet, 2 packet, 3 packet, 4, so on and so forth. So no decimals, no fractions. We're just going to keep these whole. And what this quantization does for these values is it restores the conservation laws. All right. So thumbs up if you're still with me. All right. I like thumbs up. I love these. So there's that. But I think the most important and most fun thing actually happened in about 1801 with Young's double-slit experiment. Okay. So we're going to start by talking about diffraction. And diffraction is just the spreading of waves around objects. So we're going to talk about light passing through a single slit. So if you're noting, you can see that the line, the beam of line is straight, the blue lines, they're straight. And then once they pass through the slit, they begin to curve and they just spread out because they're diffracting, and light diffracts around edges and through slits. But what you should notice is that this screen, I see one beam of light. And just so you guys know, this is just a pictorial representation of how this is going to work. In real life, your screen is going to be perpendicular to your beam of light or your electrons or whatever you're shooting, but I rotated it outward just so we can see what's going on. So I have, in my classical brain, this makes sense. My classical brain says I have a slit, I shine some light through it, I get a beam of light on the wall. That tracks. I like that. So using your classical brains, again, I want you to do a chat out and I want you to tell me, what do you expect to see on the screen if I have 2 slits present? So just go to the chat, type in your answer, say, I have a beam of light and I am going to shine it through 2 slits. What should I see? What do I expect to see? So I'll give you a couple of seconds, about 10 more seconds to tell me what you expect to see on the screen, and then we're going to talk about it. All right, so go ahead and wrap up your answers. We're going to do this chat out in 3, 2, and 1. Press enter. 2 beams, 2 beams. I love it. So I agree with all of you. We are all in agreement. I should see 2 beams. I love that for us. Well, here's what happened. So this is the theory. This is our hypothesis, right? This is not what we see. Okay. When we do this experiment and we shine this light through, we see something really fun. We see an interference pattern, and an interference pattern is just a alternating series of bright and dark bands that are formed by constructive and destructive waves. So what ends up happening is it passes through the first slit and you see the waves spread out. Then they pass through and they spread out again. And you can think of this as ripples in a pond. Okay, but what ends up happening is the constructive waves bolster one another, which gives us our bright fringes. And then our destructive waves cancel each other out, creating dark. And then they taper out at the end. So this is what you see. This is the interference pattern for a wave or a beam of light passing through a double slit. Perfect. So let's change it from a beam of light to, let's say, cannonballs. So let's say I have a machine gun cannon and I am just going to fire these babies right through. Now they cannot shoot through the wall. I know they're cannons, but they're gentle cannons and they like to choose directions. Okay, so stick with me. So they're either going to pass through the left slit or the right slit. So using your predictable classical brain, tell me what should happen with these cannonballs. What should I see on the screen if I'm shooting my machine gun cannon. All right, so go ahead and type your answers. Let me know. I'm shooting cannonballs through the slits, through the left or right. What should I see? And press enter now. Oh, some people are still typing, I see. The wall would break. I just said ignore the fact that they're cannonballs, but yes, in the literal sense, the wall would break. But what we would expect to see is two paths. Either the cannonball has passed through the right slit or the cannonball has passed through the left slit. So now let's make this equivalent to a modern day double slit experiment. Okay, I have an electron gun and I'm going to shoot these individual particles into the slit towards the screen. All right, so I'm going to choose individual particles and I'm going to shoot them. And so this is what I should see, right? Because these are now my little quantum cannonballs. I should see two lines on the screen. Nice and easy. I love it. I love it. So no, that's not what I wanted. Instead of getting two lines from these electrons, it turns out that I'm still going to get an interference pattern. I'm still going to get an interference pattern, but that doesn't make sense. That doesn't track. Why? Why would I get an interference pattern from individual electrons? Well, this is where we really start to talk about what quantum mechanics is trying to tell us and what it's demonstrating. So what we're seeing is some very strange behavior. So this experiment has been done 1,000,000 times, and it was done in 1989 by Hitachi. And so what they did was they closed the right slit, they opened the left one, and they observed. And what did they get? They got one path. They said, cool, all right. So they decided next, they said, well, let's close the left one, let's open the right. And again, one path, right? Easy peasy, I like that. They closed the paths off, both slits. Well, they're not ghosts. So naturally, there was no signal. Nothing happened on the screen. And then they opened both slits and they saw this. So this video is basically the video from the Hitachi double slit experiment. And what they're doing here is this is the screen receiving information from the electron gun, passing through the slits, right? And both slits are open at this point. And if you keep watching this video, something very interesting happens because I'm talking about quantum cannonballs here. I'm talking about electrons, which are particles. And as you're watching this video, you're noticing that this interference pattern begins to show up through these electrons. So if you're patiently just sticking with me, and I appreciate it. Slowly, so we're gonna get bands with heavy populations of electrons, and then we're gonna get some gaps, and you can start to see the interference pattern show up right in the middle, right? It's bananas. So you see, where's my spotlight? Don't erase spotlight. Here, so you have light, you have dark, you have light, you have dark, you have this interference pattern, and it's fantastic. This is where I get really excited about physics, okay? So what this began to introduce is this wave particle duality. And it's saying that these electrons are behaving as waves. But how is that? Because we know that they're particles. So the wave particle duality theory was introduced by Louis de Broglie in 1924, and it was based on Einstein's earlier theories, primarily the photoelectric effect, which we will talk about in the next slide. And it basically says it's a fundamental property of both light and matter, where they can exhibit wave and particle behavior. But this is kind of like an incomplete picture because this is the best our language can do to explain how this works. It's a duality, but it's neither a particle nor a wave when it happens. It's just both. So just a quick reference to the photoelectric effect. Electrons are emitted from matter by absorbed light. So basically you have light coming in, it strikes the surface, and then the electrons within the surface get enough energy to be emitted. This is the photoelectric effect, but the main important part about it is that it proved the particle nature. So this was the piece that de Broglie needed in order to create the wave particle duality. He needed somebody to prove the particle one portion of it, which is what Einstein did. But as I said, it's an incomplete view because think about it like this. If I have a cylinder, right? And I take a flashlight and I flash the light on the cylinder, depending on which way I'm holding the cylinder is going to dictate what the shadow is going to look like. So if I hold the cylinder upright, it's going to look like a rectangle in the shadow, right? But if I switch it and turn it 90 degrees, then it's going to be a circle. But we all know that a cylinder is neither a rectangle nor a circle, but it is also somehow both. And this is what we're getting at when we talk about the wave particle duality, having a bit of an incomplete view, but it serves its purpose here. Okay, so we're going to get into some stranger things where things just start to get really wonky. So again, close the right, open the left, fine. All of the particles will travel through the left. Close the left, open the right, all the particles will travel through the right. Close them both, sure. Both open, yes. So we said fine, 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 fine. Let's talk about what's happening here. If I have both slits open and I'm shooting electrons through, the electron is doing something really strange, and I have to account for that. So the way we've accounted for that is the idea of superposition. And superposition is the ability of a quantum system to be in multiple states at the same time. So it's analogous to a coin flip. So if I flip a coin way up in the air and it just flips infinitely, just flips, flips, flips. The entire time it is in the air flipping, it is in a state of superposition because it is both heads and tails. It has not decided what it's going to be because we haven't dropped it to the ground to force the measurement. Okay, so this is what the electron is doing. When we're talking about an electron being in superposition, it's somehow deciding that it's going to pass through both slits at the same time. So we said, fine, fine, Mr. Electron, that's fine. We can be in superposition. Another way you might be familiar with superposition is Schrodinger's cat, right? If you're familiar with Schrodinger's cat, it's about a cat that's in a box that's both alive and unalive at the same time. Now, if you've never seen Schrodinger's cat, don't worry. I have a surefire recipe here for Schrodinger's cat. It's really easy. You're going to need one steel box with a release on the inside. You're going to need a cat. You're going to need a vial of poison, and you're going to need a radioactive atom. Now, the prep time is going to vary. It depends on how long it takes you to catch a cat. I have two back here, but they're not for experimental purposes. So it might take me a little longer to perform this experiment. And usually the wait time is about 1 hour once you get all your pieces together. But the idea of Schrodinger's cat is that I've placed a cat, a radioactive atom, and a vial of poison within a steel box. Okay, and I've attached the hammer to some release that's triggered by the decay of the atom. There's a Geiger counter in there too, because we're scientists and we have to have some detection method in there, right? So I put everything inside the box and I'm going to wait for the atom to decay or not, because there's a probability that the atom will decay and then there's a probability that the atom will not decay. But while this box is closed, I don't know what's happening. If the atom should decay, the trigger will release the hammer will crush the vial of poison, and the cat will be unalive. All right, but because I can't open this box to look, all I know is that the cat is both alive and unalive at the same time. No cats were harmed during the making of this slide. All right, but the key piece of information here is that I don't observe what's going on inside. It's very important that I don't observe. So hold on to that and tell yourself, do not observe, just don't look. All right, we're just going to mind our business for a few minutes while we move on to some other things, but we will come back to the observation piece because it's very important. So when we're talking about superposition, it's very important to know what superposition is because it pertains specifically to qubits. And qubits are physical carriers of quantum information. They exist in, they have spin of 0 or spin of 1. All right, so they exist in these two spaces at the same time. It's like the coin flip. And the only way that they collapse or become 1 or 0 is if we look at them or observe them. All right, so a little bit more about qubits. They're the quantum mechanical analog of a classical bit. And so classical bits are either 0 or 1, whereas qubits exist in a superposition at all times. They can't be copied, which is a really cool thing, which is why a lot of quantum computing folks are really interested in it for like encryption and cybersecurity, because they can't be copied. They're always going to be unique. And then observation will collapse the measurement of a qubit. Well, what does that mean? Okay, so we have our superposition states. So it's the observation effect. And this is this really trippy effect that takes place in quantum mechanics, right? So I told you, I've shown you several times, we have this electron gun. We have these two slits. I know what I'm going to see. I know I'm going to see an interference pattern because the wave particle duality, these electrons are going to behave such as waves, and I'm going to get an interference pattern. So scientists said, electrons, I'm on to you. All eyes on you right now. We're going to watch the slits, and we're going to watch you pass through the slits. And as you pass through the slits, we're going to know how you do that wonky thing you do with superposition. We're going to know. Okay, so this was their idea. So the scientists set everything up, and they were looking at the slits, and then they said, go. And gosh darn it, 2 slits. What happened? How did I go from knowing exactly what I knew, we've seen it 1,000 times. I was going to get an interference pattern. Instead, I got this. They were just as confused as I was when I first learned this. Like, what happened? Why did we go from an interference pattern to two lines? How did this happen? Well, it's the observation effect. And what the observation effect does is that when I look, we're going to go back a little. When I look at these qubits, right, when it's in a superposition state and I'm not observing it, it's 0 and 1. But the minute I look at it, it's the equivalent to the coin coming down from the sky and hitting the ground. Once the coin falls, it can't be heads or tails. It has to be either or. With the observation effect removes the quantumness of a system, the superposition portion, and it makes it act more classically, and it has to choose. So what ends up happening with the observation effect is that because the electron knows, and I don't know how it knows because it's not sentient that we know of, because the electron knows that it's being observed, it doesn't want to be in superposition. Now it's shy, and it's like, oh, since you're watching me, I guess I'll decide whether to go through the left or the right, which is exactly what it does. So observation actually collapses the measurement of a quantum system. And this is just for a singular quantum system. Now, there's a really cool thing that happens when you get a 2-body quantum system, okay? It's called entanglement. And entanglement is a really cool phenomenon that's also based on the observer effect. And what happens is if I have 2 entangled qubits, right? Say Clarice and I are entangled. Okay, and we each get a box, and within these boxes there is a red ball or green ball. And actually, because of superposition, there is a red and green ball. It is oscillating between red and green, but we have not opened the boxes, so we don't know. Okay, now I could easily sit in the same room with Clarice, and we could both open our boxes and see what we have, right? But the cool thing about entanglement is I've gotten my box, and I've decided I would like to go home now. So I go 36 miles away from campus where I live. And I come into my house and I go, oh, look at this nice little wooden box. And I open my box. Now, remember, inside the box is a red and green ball or marble. When I open my box, the measurement is going to collapse. And that ball is going to either be red or it is going to be green, but it will no longer be both. So say I open my box and I get a green ball. Awesome. Great. I love it. But what that automatically means is that Clarice's ball has now also collapsed, and Clarice has a red ball. She doesn't know it. She won't know it until she opens her box. But my observation of my box has automatically collapsed her measurement. And so it has forced it to become a more classical system. So that's what entanglement means. It means that the state of one automatically affects the state of the other object. And then we can observe these things. So I've said a lot. And I just realized I don't think I have a full slide for everything, but let's talk about some of the things we've learned for just a minute before we do. I'm going to stop sharing so I can look at all of your lovely faces and we can discuss kind of what I talked about before I go into the next part of my presentation. Hello, everyone. Are we still with me? Are we still, things still good? I love it. Okay, so we've talked about a lot of things, but there are a couple of things that I want you to take away from this. The first thing is that quantum mechanics isn't new, right? It's something that we have had for a very long time that informs a lot of the world that we live in. That's the first thing. The second thing is that quantum mechanics, the reason that quantum mechanics is the way it is because it cannot be defined by classical mechanics. I cannot use Newton's laws to describe photons. photonic behavior or electronic behavior or particles. I just can't, because quantum abides by its own set of rules. Quantum is discrete, which means it's whole numbers only. That's how I like to call it, whole numbers only. You get single packets, maybe a double packet, maybe a triple packet, but you don't get 1.5 packets of energy, right? And a lot of the laws of quantum begin to bring together some formulations that scientists were struggling in the past. Another big thing that we talked about is the wave particle duality. It's the ability of an electron to exhibit wave-like behavior when we know that it is a particle. And lastly, superposition, which is just being everything at the same time until somebody looks at you and then you just stop being, you're just one thing. All right. Those are the biggest takeaways for quantum mechanics. And when I first started this journey with quantum mechanics, I was a freshman in college. I wasn't taking a quantum mechanics class, but we were finally touching on relativity. And like double-slit experiment, any analogous? Oh, I'll answer that, or Clarice and I will answer that in just a few moments. I enjoyed it because it was unlike anything I had ever seen, because again, in my normal life, I deal with the tangible. If I'm cooking and I touch something that's hot, I will burn myself. Not quite the same thing with electrons. I've not touched a hot electron yet. Should that happen, I will let you all know. But these concepts, these are just the main bullet points, and I will do a quick refresher before Hunter's talk next week. But these are just some of the main bullet points for a lot of the things that we're going to be talking about throughout the Fiat Lux. Before I forget, Clarice, do you want to answer the question for an analogous experiment that demos the entanglement effect?
By analogous experiment, do you mean like classical experiment? So entanglement is a merely quantum mechanical property, right? I think I really like the analogy that Jackson made, and those remain analogies. However, quantum entanglement is already harnessed in many technological applications. Those are things that exist, that have been measured, and as you're going to see going forward, entanglement underlies why quantum computing is powerful, right? So it's this very special way that many quantum objects have of talking to each other that gives like superpowers to quantum computers. If someone wants to know more, for example, there are experiments that people do in some university labs, even on entangled photons, of a pair of photons that have this very special interaction with each other. We're measuring something about one, things about the other. So there are simple ways to measure entanglement in the lab. And again, those things can be used even commercially for doing encryption. And there are actually commercial sources of entangled photons, for example, photons being the quantum particles of light. So yeah, as Jackson said, we already live in a very quantum world.
For if observation collapses a double-slit experiment, then how do we observe the interference in the first place? That has to do with the way we did. This one's finicky, because if the electron, quote unquote, knows that it's being observed, then the measurement collapses. When they first did it, they just did it. And they were not looking at the slits, and they did not have a detector in place to look at the electrons. So they just let it go naturally. And that's how we first observed the interference pattern. And then when they tried to look, that's when the observer effect came into play, because then they were like, this is weird, and this is not what we hypothesized. So then they looked, and then they got the strange observer effect. They went, thanks, okay. But the observer effect is helpful because it's a bit of what powers quantum computing, this observer effect. So it's very important that it came around the way that it did. I did see a question in the chat about recordings. for everybody, just so you know, tell all of your friends, we are recording this session. It was being recorded before you came into the room. They will be posted on our YouTube channel. Every lecture and then the slides will be posted in a drive that we will make available to you all, so you all can follow along. So you never have to worry. If you are in a time zone that's really wonky and you want to go to sleep, that's fine. It will be recorded and you can watch it at a later date. Another piece of surface level about how to create entanglement. Whew. I cannot. I'll be honest to say that I cannot explain, but that would be a great question for Hunter, who will be here next week, because we're going to get into quantum. The first two sessions is the intro to quantum mechanics, and then next week will be an intro to quantum computing. So that would be, just hold on to that question, just hold it tight, and we will answer it next week. One of the things Clarice has asked me to do is, as a part of this, but $1 is still safe like the safe. Simply don't observe. Exactly. Perfect way. Clarice wanted me to discuss a little bit about my journey to quantum, which is a very not straightforward path, but this is one of the reasons why she's having me do it. So it's actually a 3,000-mile journey. I grew up in, my dad was in the military, so I grew up all over, but I ended up going to high school in Riverside. When I was in high school, this very strange thing happened. Because I didn't know I was ever going to be a physicist or an engineer. I hated math. Like once algebra kicked in and they were like, here's letters and numbers, I was like, pshaw, I'll do no such thing. And my mom, who's in this room, can attest that all of my other grades would be like fantastic, and my math grade would be like absolutely not. So when it came time for college, I thought I was going to stay in California. My mother had other plans for me, and she told me I should apply to historically Black colleges and universities, which are all in the South and on the East Coast. I think the closest one to us is in Texas. So I applied to Hampton University, and I am a horrible saboteur because I really tried to sabotage this application, guys. I swear I tried to sabotage this application because I did not want to leave California. And I still got in. So if you want to know how bad I am at sabotage, there you go. All right, so I got into school. So I flew 3,000 miles away and I went to Hampton University. So my path to quantum was very simple. All right, despite what my mother told me about accepting free food from strangers, on my first day on campus, somebody said, hey, you want to come to the physics open house? And I said, absolutely not, because I hate math. And they said, there's free food. And I said, well, I'll be there. And I call this, if I wrote a research paper about it, it would be the Pavlovian effect of food on nutrient deficient students, because it does not matter how well fed you are. As a freshman in college, I don't know what it is about college campuses, but the moment you step foot on a college campus, you will be the hungriest you've ever been in your entire life. The minute you become a student, all bets are off. You always have to know where the free food is coming from. And this is how they got me. All right. I ended up going to this open house with two women, one named Jan Mangana, who was the program coordinator for the department, and another woman named Claudia Rankins. And that name might be familiar because she just recently retired from NSF after leaving Hampton. And first off, it was two women, which was like amazing. It was a Black woman and this wonderful German woman. And they were talking about, you want to be a doctor? Do physics. You want to be a lawyer? Do physics. You want to live your best life ever? You will do physics. And by the time my plate was empty, I was signing on the dotted line to change my major. This is how they got me, with free food and the appeal that anything could be done with physics. And by the time I realized what I had done, it was too late to leave. So just joking, I loved it. I ended up getting my degree in physics and minoring in math. And I studied accelerator physics, which I truly enjoyed. So then after Hampton, I did a whole bunch of other things for a long time. I was a teacher. I was a bartender. I actually ended up teaching at a bartending school. I did a lot of things. And then somehow I ended up at UCLA as a admin in the Women in Engineering department under Audrey Poole O'Neill in Women in Engineering, where I met Clarice. After meeting Clarice, this is exactly how this went. She said, hey, you want to get a PhD? And I said, no. And she said, there's quantum biology. And I said, I like that. So this is my very roundabout way to a PhD program that I had not intentionally or had not considered, because I do love the idea of quantum biology and the idea of magnetosensing. And essentially what I am studying is if the biological functions that we use in order to live our lives are indeed facilitated by some quantum mechanics. So I'm wondering if really small scale quantum science affects huge macro scale biological functions. That's really the main bullet point of what I'm doing. And it's awesome. So this is a very transparent moment because I tell everybody that science is for everybody. So one of the main things I learned coming to graduate school is that I do have ADHD. It probably would explain a lot of things about my life. I just thought my brain was my brain. But coming to graduate school, the reason this slide is important is a lot of people and a lot of depictions that we have of scientists are that scientists are these perfect individual beings. Everybody's brilliant. Okay, everybody has their head on straight and everybody does exactly what they're supposed to do when they're going to do it. And there's no issue. Well, that's not true because I do have a degree in physics and I am getting a PhD in electrical and computer engineering. And my brain doesn't always do the things that I would like it to do when I need it to do it. And so graduate school was a big journey of self-discovery because I was able to learn that I had ADHD. And so my biggest thing for me, if you read my bio, is that I am a huge advocate for science, and I'm working on a series about a young girl who does science. And all of this is relevant to her experience because I think it's important for every person in this room to see somebody that has something that's not the perfect scientist. And I'm not Sheldon from the Big Bang Theory. I'm not even Leonard. My mother says I'm more Leonard, but I'm not even Leonard, Kutherpali, or Howard. I am pretty much just me. I don't know everything. I work very hard to learn the things that I know. So what I want everybody in this room to take away is that there may be something different about you or something that sets you apart when you're in a room. You may not look like everybody else. You may not sound like everyone else. You may not have the same background as everyone else, but you still belong there because the important thing about this is that science is absolutely for everyone. And all that matters is that we let people do the science. So that is me. I would like to open up the floor for questions about either my journey or quantum mechanics. I will answer them to the best of my ability. Thank you. Oh my gosh, okay. Yes, awesome degree choices. Thank you very much. Thank you, everyone. Were there any questions? You can raise your hand. You can just unmute yourself and blurt it out. No holds bar here. We welcome all the participation. Questions, comments, concerns, fears? I'll stop sharing so I can see just in case there's hands raised that I cannot see. Well, if there are no questions, I am going to turn it over to Clarice in a minute if she has any closing remarks, but I do want to thank each and every one of you for being here for our first Fiat Lux of the spring. Yay, we are very happy to have this available for you all to see these different speakers. Next week will be Hunter Solomon coming to talk about quantum computing. He's very excited. I'm very excited to have him. I do see some things happening in the chat. Applications of quantum biology, sure. So applications of quantum biology. So for what I'm studying, it's magnetosensing in migratory species, where we are seeing if the weak magnetic field of the Earth is dictating the chemical reaction in the brain of a bird and telling it and informing its inclination compass. So birds have inclination compasses, which tell them which direction they should be traveling based on the orientation of their orientation with respect to the magnetic field. So that's one thing. On a bigger scale, if you can start to use quantum mechanics, quantum biology, you could start talking about medications. You could start treating cancers, start doing a bunch of different things, talking about metabolic functions and reductive oxygen species, where we're like using antioxidants better so the human body can kill the cells that aren't good for it, things of that nature. So there will be some applications of it. Current applicable tech, I'm unsure. Clarice, is there current applicable tech for QM?
Yes. Yes, for example, if nature is using quantum mechanics to function, this means that it knows darn well how to deal with noise. And as Jackson was saying, everything that starts quantum dies classical, and that's the reason why we live in a classical world, right? So, and that's the reason why quantum computers are not perfect as of yet. So we're not saying, well, let's replace Google's beautiful quantum computer with a molecule, but rather, are there techniques employed by nature on how to deal with noise that could then be employed on top of existing quantum computer technologies, for example? So that's one way that learning with nature could help build better technologies, or how to use sensing mechanisms using biological quantum objects on how to build like better sensors and so forth. Yes.
Awesome. Thank you for that, Clarice. I have nothing else to impart except that join us again next week at noon for Hunter Solomon's talk on quantum computing, which will open up more doors and more gateways to some quantum mechanics and some specific things that happen in the quantum world. And we'll make way for some of the other series that we're going to see later. Thank you all for joining us. Clarice, did you have anything else you wanted to add?
No, again, Jackson, you're awesome. You're like, I think everyone knows how awesome you are. I just wanted to mention in front of everybody how awesome you are. And we want to make this Fiat Lux class as open to anyone as possible, right? So that we can share why we love quantum mechanics so much. So please help us spread the word, spread the word, yes, about the Fiat Lux class. And I think that's it. And thanks for your attention.
Thank you guys for coming. We will see you next week, and you can find us on YouTube. We'll be posting this up over the course of the next 2 days. Thank you all. Thank you all. Have a great day. Thank you.